Hello and welcome to this video about polynomial data structures. In this video, we'll create a function that can perform polynomial division. Because most polynomials don't divide evenly, then we'll have both a quotient and a remainder polynomial. As an example, to see what's involved, we'll divide this longer polynomial by this shorter one, so as to study what the program has to do. So the first step is to divide the leading term of the dividend polynomial by the leading term of the divisor polynomial. It divides evenly. 35 divides by 7 to give 5. And we can also divide the powers of x here to give us x to the fifth. Then we'll multiply the whole of the divisor polynomial on the left by this term to give us this polynomial. We'll write it underneath so that all of the same powers of x are in each column. Then we'll subtract the bottom polynomial from the top to give us this polynomial. Notice that this eliminates the leading term in the bigger polynomial. We'll keep doing this until we've worked our way across the whole polynomial. Then we'll drop this term down to be next to this polynomial to give us a new polynomial with 3 terms. So then we'll divide the leading term in this new polynomial by the leading term in the divisor. It divides evenly to give us this number. We'll then multiply the divisor polynomial by this term to get this new polynomial that we'll write underneath, keeping all of the powers of x in the same columns. Then we'll subtract these 2 polynomials to give us this polynomial. We'll drop this term down to give us this new polynomial with 3 terms. Then we'll divide the leading terms to give us this term above the line. We'll then multiply the divisor polynomial by this term to give us this polynomial that we'll write underneath. So we'll skip a lot of the steps until we get down to this part of the long division process. Then we'll drop down this term. We'll then divide the leading terms to give us this term, which is a constant. Then we'll multiply the divisor polynomial by this constant term and place it under this other polynomial. And because these 2 polynomials are equal, they subtract from each other to give 0. So now we're finished. The quotient polynomial is on top of the line, and the remainder is at the bottom, being equal to 0. Now to look at some code that divides one polynomial by another. It contains some complicated loops, like you could imagine, but it isn't all that long or complicated. We'll declare the function with all of its internal variables. The function will divide the polynomial px by the polynomial qx. We'll return the quotient and remainder in these 2 other polynomials, called quot and rem. We'll look at some special cases. We'll look at the case where the divisor is a constant. The length of the dividend doesn't change in this case. So we'll make up a simple loop to divide all of the terms in the dividend by the constant term. And the remainder will be 0 in this case. Then we can leave the function early. Another special case is where the dividend polynomial has a smaller degree than the divisor polynomial. The remainder is equal to the dividend. The quotient is the 0 polynomial, or we could just say 0, but the degree must be set to 0. Some mathematicians would set the degree to be minus infinity, but setting it to be 0 is practical for this function on this occasion. And then we can leave the function early with this return command. So now we're going to do the general case, where the code is quite complicated. We'll copy the dividend polynomial to the remainder polynomial here. Then we'll set this variable, which is the leading term of the divisor, which doesn't change during the cycle of this function. We can get the degree of the quotient polynomial here straight away. We'll set all of the coefficients of the quotient to be 0 to begin with. It isn't necessary, but it's good if you want to check and debug the code. And so now to create the loop to do long division. I is the index variable to the dividend polynomial as we work our way along it and keep subtracting the leading term. This is the part where we'll divide the leading terms by each other. We'll put this value into L ratio, which stands for leading ratio, because it's the ratio between the 2 leading coefficients. This is the part where we'll place the term in the quotient above the line. And this is the part where we'll subtract the multiple of the divisor polynomial from the dividend. And then we'll decrement these indexing variables to point to the next non-zero location in this polynomial, and its degree will decrease by 1, eventually becoming the remainder polynomial. Because we'll be subtracting two polynomials, the possibility is there for this polynomial to have the first n leading coefficients being equal to 0. We'll have to decrease the degree of the polynomial in this case, and it is done by this function. Now for the function to eliminate the leading zeros from the polynomial. We'll declare it as usual. We'll set this indexing variable to be equal to the degree of the polynomial that we want to perform this function on, which is the remainder polynomial. This loop will decrement the variable I whenever the next leading coefficient is 0. And so we'll set this degree equal to this new amount. We've successfully eliminated the leading zeros in this polynomial. Now we'll create a function to create a random polynomial with degree n. We'll set its degree here. Then we'll use this loop to fill its coefficient array with random numbers. We'll make up a simple function to multiply a polynomial by a constant. We'll set the degree of the new polynomial here. And we'll fill its coefficient array with coefficients of the polynomial multiplied by a constant. And here are two functions to test whether two polynomials are equal to each other. Firstly, their degrees must be equal. And we'll make a loop to check each coefficient of each polynomial. Their arrays are of the same length because their degrees are equal. And we'll check that all of their corresponding coefficients are equal, and if a pair of them aren't, then we'll leave the loop early. And we'll return the value of the return variable here. And this function checks whether a polynomial is equal to 0, or the 0 polynomial. Its degree must be 0, and its first coefficient or constant must also be 0, otherwise it'll return false. And we'll return true here if it is the 0 polynomial. Now to test this function, to see whether it is operating correctly. We'll do this in 4 parts to check the 4 types of data. In the first part, we'll divide a longer polynomial by a shorter polynomial, so that they'll produce a non-zero remainder. We'll test 100 random samples, and this goes fairly quickly. We'll get 2 random numbers for the degrees of 2 polynomials. Then we'll get the minimum value of these 2 numbers. And this new random number that's smaller than the other 2 will be the degree of the remainder polynomial. And so we'll create all 3 of these polynomials using the random function. We'll copy one of these polynomials to another polynomial so that we can recall it later. Then we'll multiply 2 of these polynomials together, and then add the remainder to it. Then we'll divide this new polynomial by one of the polynomials that we've generated earlier. Then we'll copy these polynomials to get ready to use the equality function. Then here is where we'll test if the quotient of the division function is correct. If it isn't, we'll print out an error message. And here is where we'll check if the remainder is correct, and we'll print out its corresponding error message if it isn't. So this is the second part of the testing function, where we test the division function with a 0 remainder. It's just like part 1, only we don't add on a remainder polynomial after we've multiplied 2 random polynomials together. So we'll create 2 random polynomials and copy one of them to another polynomial so that we can recall it later. This is where we multiply 2 polynomials together. And then we'll divide one polynomial by another. We should get one of the random polynomials that we created at the beginning back again. So then we'll call these copy polynomial routines so as to get ready to test if 2 polynomials are equal. Then we'll test to see if the quotient polynomial is correct. Then we'll test to see if the remainder polynomial is correct. It should be 0. So now we'll test the division of a polynomial by a constant, which is a degree 0 polynomial. we'll get a random polynomial with a non-zero degree. Then we'll get a constant polynomial. Then we'll copy a polynomial to another polynomial so that we can recall it later. Then we'll multiply a polynomial by a constant. Then we'll divide this polynomial by a constant polynomial that is equal to the constant that we multiplied the polynomial by in the first place, which should give us this polynomial back. We'll recall the first polynomial that we created using the random function, and use another copying function to get ready to use the equality function. And finally, we'll test that the quotient and remainder polynomials are correct. And finally, we'll test the division function when the dividend has a smaller degree than the divisor. We'll get these two random numbers. Then we'll arrange them in order so that one is always bigger than the other. Then we'll get these two polynomials so that the divisor is always larger than the dividend. We'll call the division function. Then we'll test this function for correctness. The remainder must equal the dividend, and the quotient must be 0. So let's try a quick trace of this program. LQ is the leading coefficient of the divisor, and remains unchanged throughout the entire running of this function. So let's have a peek at what is happening in the code in terms of an actual long division process. We're ready to subtract these two polynomials. And so we'll subtract them, and so this polynomial is shorter, and this is where the subtraction is done in the code. We'll drop down the next term in this polynomial, which the code doesn't need to do, because the whole polynomial is dropped down in the code. We'll represent this decrease in the degree of the polynomial here by decrementing the degree attribute and indexing variable. We'll get this term here, which is equal to the leading term in the dividend divided by the leading term in the divisor, so we'll add it onto the quotient polynomial. This is represented by these two lines of code. Then we'll multiply the divisor by this term and get it underneath ready to subtract it. This part of the code represents this multiplication. So then we'll subtract it, which really takes place in one step in the code. This part of the code represents this subtraction. Then we'll drop the next term down. The computer doesn't need to do this step, but we do need to decrease the degree of the polynomial in the code. We'll get the ratio between the two leading coefficients of these two polynomials and insert it into the quotient. Then we'll multiply the divisor by this term and get ready to subtract it. And so then we'll subtract it. It takes place in one step. So I'll just mention here that the polyadd function needs to call this eliminate leading zeros function at the end, because it is always possible that when two polynomials are added together, then the degree will be less than either of them, because their leading coefficients will cancel out to make 0. And we'll similarly do this for the subtraction function. So I hope that you have found this video to be helpful, interesting and educational. Please click like and subscribe if you did. Please leave some helpful thoughts and ideas in the comments. Feel free to share this video or any of my videos on this channel, and thanks a lot for watching.